Hey, so today I'm going to talk about how wheels work and why do we have wheels, and really the reason we have wheels is in part to deal strategically with friction. It's not just to get rid of friction, it's to work with it in a way that allows us to have vehicles that move, or carts and so on. So that, the physics story is in large part about what friction is and how it works, and also a little bit about the consequences of friction. So, okay, so let me start off with a question just to get us all thinking about this. Here's a fairly simple question to think about. You're at a red light driving a car, and you want the car to accelerate forward when the light turns green as quickly as possible. So the question is, do you want the wheels to actually skid on the pavement as they try to summon forward forces out of it? Or do you want the wheels to just barely avoid skidding? So hopefully you can picture skidding. You've seen this in movies or something like that, or maybe you've done it yourself, where you actually get the wheels to move across the pavement and leave black rubber marks. So which of the two is the best for accelerating fast? Any questions with the question? Okay. So we'll go to the 30-second point and call it. Five, four, three, two, 1, 0. And the majority are going for B, and that actually is the better answer. The reasons for the difference are not obvious, and so they're part of the story today, but it turns out that you really don't want to spin the wheels on the pavement. There are times when they do, and actually I can say that. The drag racers, if you ever watched a drag race live or on video, they deliberately do spin their wheels, at least when they're literally warming up the wheels, and they're trying to make their wheels essentially sticky, which is a complicated story, but there are occasions when skidding your wheels is okay, is a good idea. But for the most part, with ordinary tires and ordinary cars, you don't want to do it, in part because you don't accelerate as fast, for reasons we'll see in a minute, and in part because it wears out your wheels. That burning rubber literally burns rubber. You're actually damaging the wheel, and in principle the pavement of the road as well, and you get less mileage out of the tires, so not a great idea. Okay, so the part of the story though is to figure out why what's wrong with burning rubber and so on. So first part of the story is what is friction. And I told you some days ago about we encountered support forces. When I put a wagon on a sidewalk, the reason the wagon doesn't fall through the sidewalk is because the sidewalk and wagon push apart. Occupying the same space at the same time is just not something our universe likes. So it pushes them apart, and those support forces that showed up from the table on the wagon, from the wagon on the table, they're exactly perpendicular to the surfaces. So in the case of this horizontal table, sidewalk, whatever it is, the forces that we call support forces from the table, they're straight up. That's the only direction that support forces know about. And from the wheels of the wagon, it turns out the very bottom surface of those wheels is horizontal. If you zoom in there with a microscope, you say, oh, the wheel is bending up, it's horizontal right there. So it's pushing straight down. So those are support forces. Well, there's another major direction between two surfaces, which is along them rather than at right angles to them, perpendicular. And the forces that are at right angles, that are along the surfaces, parallel to the surfaces, are all known as frictional forces. And they're, frictional forces plural because there are a couple different kinds of friction. And actually, there are more kinds than I'll talk about. So what I'm giving you will be, in some respects, an approximation. People who are experts in friction will identify a variety of other possibilities. But all the forces between two surfaces that are along those surfaces are frictional forces. And they have frictional forces sort of have a universal, probably the experts would say no, it's not completely universal. They're weird counterexamples. But frictional forces have this interesting capacity to figure out which way the two surfaces are moving relative to one another, assuming they are moving, and to fight it. So that if I scoot the wagon to the right, it's slowed to a stop. Well, I got it moving to the right, which is sort of before the story started, and something pushed it to the left to cause it to accelerate leftward and therefore come to a stop. The something that pushed leftward is a frictional force. The table exerted a leftward frictional force on the wagon. Is that okay with everybody? If I scoot the wagon to the left initially, now the frictional force again appears, but this time it figured out that it's going to push to the right and slow the wagon to a stop. So basically, it's always trying to stop the wagon, no matter what I do. Backwards, forwards, friction is intelligent. Well, obviously not really. So how does it figure this out? What friction is trying to do is it's trying to bring the two surfaces to the same velocity, whatever the pairing is. And the details of who slows down, who speeds up, and that's part of a more complicated bit of the story. But the basic story is whatever the two surfaces are doing, it tries to bring them to the same velocity. If they're already at the same velocity, they stay there. If they were moving relative to one another, so from by which I mean, if we're the table and the wagon is moving to the left, according to the table, push the wagon to the right. On the other hand, if we're the wagon and let's be the wagon here. If we are the wagon, now as we're moving with the wagon, we try to bring the table up to the leftward movement of the wagon. What I just encountered and should say 2 cents about is friction forces, like everything else, appear in pairs. So the table has been pushing on the wagon, and we can see its effect on the wagon. But the wagon is also pushing on the table, and we don't see that so much because the table is all bolted together, connected to the floor, connected to the earth. The whole earth is responding to the wagon's push, and not much is noticeable. But the point is that the two are trying to go to the same velocity. If I deal with two objects that are of more comparable mass, the fact that they're pushing on each other would be more noticeable. I don't have any obvious choice for doing that. But so you can feel with your own hand, if you try to scoot one hand across the other hand, they both push on each other, and the goal is always to move together. We're okay with that? I won't beat it to death any further. All right, that said then, frictional forces always act to try to either keep two objects at the same velocity, if they're truly moving together or not moving at all, or to bring them to that same velocity. But there are two different kinds of frictional forces that show up immediately in this part of the story, and that is you can have frictional forces that are associated with two objects that are not actually moving across one another. They're just trying to stay at the same velocity. And talking about it as velocity, it may seem like an awful fancy word to be using for this situation where the wagon is the wheelless wagon. I always feel sorry for this wagon, having never installed its wheels. Sorry. You're special. Okay, so this wagon has always, it's at rest right now, and it's staying at rest. And interestingly enough, it will stay at rest even if I pull on it. Let me add a little weight to the wagon so it's got something to do. And now if I begin to pull on the wagon, which I'll do with a scale. And the point of using a scale is it'll tell us how hard I'm pushing. In fact, in newtons, for better or worse. But here I can see how hard I'm pulling. I'm pulling. Right now, nothing. Now, I'm up to 2 newtons. I'm up to 4 newtons. I'm up to 6 newtons. I'm pulling to the left moderately hard, and nothing's happening. So you know what the table is doing. The table is pushing to the right with 6 newtons, right? It's matching me. Whatever I do, 6, 8, it's matching me again. So this force of friction between two surfaces that are not in relative motion yet, it's got a name, okay? It's called static friction because it's static. Static friction is adjustable. It will exert a variety of forces, just the right amount to keep the objects from moving relative to one another. The table, because table's not going to go anywhere, so the wagon loses this battle. The wagon is going to, static friction is going to try to keep the wagon stationary. So I'm up to 10 newtons, I'm up to 12, and last I remember, somewhere around here, it broke free. Oh, look what happened. Suddenly, at about 14 or 15 or 16 newtons, static friction gave up. Can't do it anymore. And the wagon, really, I guess it's appropriate to say, it broke free. It managed to begin to move, and once it began to move across the surface, I could keep it moving. You know, watch the continued movement. I could keep it moving with only about 10 newtons. There it goes. About 10 newtons is all it's needed to keep it going. And when it's moving at constant velocity and I'm exerting 10 newtons on it, you know what the table's exerting on it. What's the table exerting on it in that direction? 10 newtons, right? I don't have to like overcome something. I just have to balance it. So I was pulling to the left with 10 newtons because friction, now the friction it does involve relative motion, so it's got a new name. It's called sliding friction, or you may have encountered it as dynamic friction. The new friction that showed up was pulling to the right with 10 newtons. So the two of us were pulling on the wagon, fighting over it. 10 newtons each, cancels, that's nothing, and so it was coasting. So just to make sure the story's all clear, having several things happened in close sequence. Initially, the wagon was just sitting there with no force on it at all. Horizontally, nobody was bothering it. I started to pull. Friction, static friction compensated for me, canceled me. So I pulled with 2 newtons. The table exerted a 2 newton rightward static frictional force. Lots of words. I pulled with 4 newtons. It pulled with 4 newtons. 10 newtons, 10 newtons. 15, 14 and a half newtons, 14 and a half newtons. And finally at 15 newtons, it broke free. And why broken free? It's because the friction comes about because microscopically these surfaces are not absolutely mirror smooth. They're not glass. In fact, they could be glass, and even then, microscopically, they're not smooth. There's always structure at the finest length scales, at the tiniest details, and those two surfaces then sort of interdigitate among one another, like the bristles of a brush, of 2 brushes. Imagine 2 hair brushes. Always talked about this and then never brought 2 hair brushes in. But imagine take 2 hair brushes, face their bristles into each other. They'll get kind of locked together. And as you try to drag one of the hair brushes across the other hairbrush, it's tough. They fight because the bristles hit each other and push. And that's like static friction. Those bristles are kind of interlocked and you can't get the whole thing going until you pull hard enough and suddenly the bristles begin to bounce off each other and move through each other. That moving through each other might break some of the bristles, things are actually bouncing around, really. And now you've got sliding friction. And I got up to the maximum of static friction, and it broke free, and then it was going along, and now the bristles are having left, they're not interdigitating as much anymore because they're kind of bouncing along as it moves. And then you get sliding friction. And sliding friction, in general, not always, but in general, is weaker than static friction. So the strongest static frictional force I was able to get out of the table on the wagon was about 15 newtons, right before the wagon broke free. After that, I got a weaker force. And this actually is why, this is the answer to that first question I asked you, or the underlying concept behind the first question, where I asked you, do you want to skid your car, you want to burn rubber as you're starting your car forward at a green light, or do you want to just barely not do that? And the reason you just barely want to not do that is because you're trying to make the car accelerate forward. So I'll give you the whole story, and hopefully it's followable. You try to make the car accelerate forward. You need, therefore, something to push you forward. What are you going to get? I mean, apart from having someone rear end you, which would work, you look for the only things around, which are, the pavement. So you push the pavement back. That's your car, you and your car. You are your car, and just let's live with that. So I'm the car. I push back on the pavement with my foot. It cannot help but push forward on me, equally hard in the opposite direction. The force I'm using initially is static friction. My foot or tire is gripping, interdigitated into the pavement. We're gripping tightly. I push a little, I get a little force. I push more, I get a bigger force. Bigger. We're working our way up in the world of static friction until finally I reach the very most that static friction will give me, and I haven't quite broken free. And if I do this, I accelerate forward with the biggest forward force I can summon from the pavement. It's a frictional force, it's a static frictional force, and it's as big as I'll get. If I break free, I push a little harder, and my foot begins to slide, which is equivalent to the tire beginning to spin and skid. When that happens, now I still get a forward frictional force, because I'm still exerting a backward frictional force on the ground. It's exerting a forward frictional force on me, but it's not as big anymore. Is that okay? So you tend to want to avoid sliding friction if you're trying to undergo the biggest accelerations, where you're trying to summon the biggest forces you can out of a surface, whether it's on a bicycle, your shoes, any of that stuff. Ideally, you want static friction. Once you begin to slide, you get weaker forces available to you, and they can become quite weak. I told you that there are a lot of frictions around. One of them that you've encountered from time to time is the friction that shows up when you've got a liquid layer on the floor. This is under the theory that this class is supposed to be useful rather than covering some specific curriculum. You've had this experience where you walked on a floor and said, whoa, suddenly it's really slippery. It doesn't take very many layers of water molecules on a surface before you are not standing on the floor anymore. You're standing on water. How many water molecules? A couple, like 3. And nearly everything in this room, or nearly everything in this room, has at least like one layer of water molecules stuck to it because they just like to stick. Water's everywhere, right? And water loves to stick on surfaces for interesting reasons that have to do with the sort of the chemistry of the surfaces. And it doesn't take very many more water molecules to layer on there. You put a second layer, a third layer, now you got a water layer. And suddenly you are not standing on a solid anymore, you're standing on a liquid. And you lose friction very easily in that context. So the friction that's associated with having two surfaces that are wet, it's not static friction, it's not sliding friction, it's another story. And it's typically very wimpy. And that's why you want to avoid it. Okay, so back to ordinary frictions, static and sliding. So we see that in general, just sort of want to tally up factoids. Static friction is typically better than you'll get stronger than you get more traction out of static friction than you will out of sliding friction. The nature of the surfaces matters. Rougher surfaces tend to give you more of both of those kinds of frictions than very slick surfaces. You know that probably from experience, that if you want to keep people from accidentally sliding as they go up and down the staircase, say outside this lecture hall, you put rough surfaces on the steps. So the steps have these abrasive coated tape surfaces there to try to give you better traction. The other thing that matters in how much friction you'll get is how hard the surfaces are pressed against one another. The harder you press them against one another, the more of these little interdigitating contact points show up. Basically, you're shoving the bristles deeper into each other, and you get more grip that way too. And to a pretty good approximation, it's just an approximation, the strongest static frictional forces you can get, and also the sliding frictional forces you'll get, are proportional to how hard you press the two surfaces together. If you double the push between the two surfaces, you double the static frictional force. You also double the sliding frictional forces you get when things start sliding. It's pretty good. So for example, I know this guy, I got to 15 newtons with the 5 kilogram blockhead in there. If I put the 10 kilogram guy in there, my guess is I'll get to 30 newtons before I get it to skid. Let's see how that works. This is one of these cases where experiment gets to say whether the theory is right or it's wacky. See, I'm going past, this is now a bigger scale. There's 10 newtons, there's 20 newtons, so I've already gotten more static friction force than I got with the little 5-pound cube. Sliding kicked in right after I got past 20. Yeah. I also had to sort of let the thing settle. It's really trying to interdigitate. So once you've got it sliding, you have to wait a little while. Okay. 22, 24, oh, I got about 24. So I roughly doubled the static friction force, and not quite. You know, it's a approximation. So where does that matter? It matters, for example, in cars on days when you're having trouble getting traction, like there's snow and stuff around. The frictional forces that are available to you get stronger as the car is pressed more tightly into the pavement. And in the old days, the older cars, say cars from 1950s or something like that, the engine was in front as usual. Most cars were front engines. But the wheels that propel the car, the driven wheels that the engine turns, and I'll talk more about that later, are the rear wheels. So those older cars, had the engine in front, the wheels that matter, that propel the vehicle in the back where there's sort of nothing over them. They were not pressed very hard into the pavement. They therefore they have very limited traction because there's not a lot of force pushing those wheels into the ground. And so you get stuck in the snow pretty easily. For example, with rear wheel drive cars, small trucks still do this. I forget who does this anymore. It was the days of having a hump that went through the middle of the car where the drive shaft would go. You couldn't see the drive shaft, but you could see the covering of the drive shaft, and no one wanted to sit in the middle seat of the rear car. Okay, important history that you don't know about. Okay, modern cars almost all have either four-wheel drive, which is just wins, okay, or they have front-wheel drive, which means that the engine spin deliberately turns the front wheels and summons the forward forces that make your car go. And sitting on top of those front wheels is the heaviest thing in the car, the engine. Electric cars, I mean, it's a whole nother story. I don't even know where to go with those. So front-wheel drive cars have always been better in situations where you have trouble summoning enough forward force to make the car accelerate forward. And they're less likely to get stuck in something because they have more weight pushing the wheels into the ground. Is that okay? One more extreme of this is if you really want tremendous traction out of the ground, and why would you want that? Suppose you're driving a race car. And the car, not only does it need to be able to pick up speed and slow down, pick up speed quickly, lose speed quickly, it needs to be able to turn quickly. It needs enormous frictional forces on the wheels to push the car and cause it to accelerate. Accelerate forward, accelerate backward, accelerate to the side. So you want great traction in a racing car. You might go around a turn so fast that you would be accelerating to the side at several times the acceleration due to gravity. remember, acceleration due to gravity is 10 meters per second squared. Race cars can easily need to accelerate to the side at 20 or 30 meters per second squared as they go around a tight turn at very high speed. They have to change their velocity lickety-split by a huge amount. Well, normal traction between the wheels and the car and the pavement, for cars, the normal traction, maximum horizontal force they can summon out of the pavement is somewhere around 60 or 70% of the weight of the car, which is, try not to get lost in the details of this, but it means that it's very hard for ordinary cars to accelerate at more than 60 or 70% of the acceleration due to gravity. Not downward, but horizontally. You can get the acceleration due to gravity easily if you drive off a cliff. You get it, it's downward at 100%, you get the whole thing. But that's not very fun. So instead, if you want to accelerate to the side, because you're turning, the most you can usually do is get about 60 or 70% of the acceleration due to gravity. Unless something else shoves you into the ground to really grip it tightly. And what race cars do to get them to get that extra shove into the ground is they use the air. They actually play upside down airplane. They take the passing air, and instead of using it to lift them in the air, to lift them upward like a plane does, they use the air to throw them and shove them into the ground. So that's the origins of some of the interesting shapes you've seen maybe on race cars or cars that are meant to go 150 miles an hour, a Ferrari, for example. Those cars work with the air to develop aerodynamic down forces that shove them into the ground so they get extra grip and they can make crazy fast turns and stuff like that. All right? So now you know. The other thing I mentioned earlier about drag racers. Drag racers, they probably do also use aerodynamic forces to shove them in the ground to get extra grip. They accelerate forward at something like 3 or 4 times the acceleration due to gravity of the whole race, which is, it's a crazy thing, the whole thing. It's got to be terribly hard on the driver who feels that acceleration as though they were being thrown into the back of their seat very hard. You felt these kind of forces, these effects when you go on a roller coaster. You go around a really tight turn, you feel pressed into your seat. Anyhow, they're experiencing that, but how the heck do they get that forward grip? How do the grip on the wheel, on the tires, on the ground, in order to get a forward force that makes them accelerate that fast? And the way they do that is they work with tires that, I guess they use them once. Those tires, they're basically driving on sticky tape. They grab the pavement like with an adhesive grip, and they're being pushed forward by glue. All right. So this is the story of friction. Having talked about all that, let me come back to reality and have you all just think about this question. Should not be a hard one. After what I've talked about, you should be able to get this guy. You're riding a bicycle on an icy road, and there is not much friction around, or you call it, probably called traction. The friction forces are small. In which situation, or plural, will that lack of friction cause trouble for you? Okay with the question? See what you think. It's not a hard question. Some of you may not read all the answers to choose too soon. Read all the answers before you get done. You guys are good. Essentially everybody's got the right answer here. 5, 4, 3, 2, 1. It's all E, right? And the reason it's E, for anybody who is missing it, is the only one of these situations, and probably the person who picked B had misread the question, not the answer. Answer B is the only one in which you're moving at constant velocity, in which you need no horizontal force at all. to continue doing what you're doing. And so answer B is the case where inertia is taking you as it had in, you're moving inertially. You need no forces horizontally. It's the other three, A, C, and D, in which you are accelerating to the side, or forward or backward. You need a horizontal force to make you change your speed or your direction of travel, and the ice won't do it. So this is sort of another one of the public service announcement ones. On this great day, the question came in, can we have class outside? I can't take the demonstrations out. I'll come back. There's some other questions I'll come back to. In any case, on an icy day, if there ever is one again, going straight at constant speed is the is when you're safest. That's true of walking too. As long as you're walking along, you're on ice and you're walking along straight and steady, you're good. It's when you try to speed up, slow down, or turn that you're asking the ice to exert a horizontal frictional force on you, and it's not so good at that. And it has to do with the liquid layers too. The surface of ice is also very interesting microscopically. It very easily becomes a liquid surface. Even though the bulk is solid, the surface can become liquid. So anyway, be careful accelerating when you don't have good traction. All right? All right, so talked enough about static and sliding friction, except let's look at one interesting situation with get the big guy out of there. We'll go back to a little guy. Okay, so I've got a question I'm going to ask you in a second. Not there. Don't have a direction. Good. Actually, I'm going to get that guy out just so it's easier. I'm going to invest energy in the wagon. Remember energy. I'm going to give it kinetic energy by doing work on it. I'm going to push it to your right as it moves to your right. I do work. It's going to leave my hand with kinetic energy, and let's watch that kinetic energy go. Disappeared. I gave it kinetic energy. I did work on it, and it moved to the right, and then pretty soon it wasn't moving to the right. Kinetic energy disappeared. Look at, having seen that demonstration without further discussing it, take a look at this question and see what you think about it. So as the box skids to a stop on a motionless table, just what I showed you, what work is done by those two objects? So does the table do positive work on the box? Does the table do negative work on the box? No work on the box? Does the box, or in this case the wagon, do work on the table, negative work on the table? All the possibilities. Which one's right? Which one actually correctly describes the work that each object is doing on the other object? And if whatever question answer you choose, you better be able to justify it by saying, here's the force that object A does on object B, and here's the distance object B moves in the direction of that force. If you can't find a force or direction, movement in that direction, be careful. If I'm lucky, I can get the graph up here, and you guys can negotiate among yourselves. Can I do this? Oh, it won't let me shrink it further. How do I get this guy out of the way? It's almost. You know, E is a crucial answer, but I can't do it. I can't hide it better than that. Don't go with popular. Popular doesn't mean correct. Yeah. All right, this may be fun, but I'm not sure it's very pedagogical. Okay, I'm going to stop, okay? We're all over the map except for B. All right, if I had F, someone would have chosen it. Okay. I'm not going to turn the lights on. You're going to do it again, but look, if I'm pushing on something and it doesn't move a distance in the direction of my force, I do no work on it. Right? I can push all I like. I can push right, I can push left, I can pull, I can do whatever I like. If it doesn't move, I don't do any work on it, positive or negative. Does the table move? And in saying this, everything, you push on things, everything moves microscopically. 0.00, if you're willing to go out enough zeros, you'll get a 1 somewhere. So I'm saying, for all practical purposes, does the table move during this little story? Does that have any influence on whether the box or the wagon can do any work, or positive or negative, on the table? You okay with the question? Try it again. Huge improvement in the choice for those of you who've chosen. 5, 4, 3, 2, 1, 0. A is the right answer. Yeah, E died off. And E died off because the box cannot do work, positive or negative, on the table, because the table won't move. So this, okay, so for those, hopefully you understand why the answer is the answer, but it raises a mystery. When I was playing with a bowling ball, I was doing positive work on it, it was doing negative work on me. And therefore, I was losing energy, it was gaining energy, the transfer was nice and complete, everything was wonderful. In this case, something in that system broke. The box, the table is doing negative work on the box, but the box is doing positive work on anything. The energy of the box is being wiped out by the negative work from the table, and nothing shows up to conserve the energy. The energy seems to have disappeared from the universe. You okay with that paradox or that struggle? Where'd the energy go? It hasn't disappeared. It's still there. It's in the surfaces, the top surface of the table, the bottom surface of the box. Those bristles, as they were bouncing against each other, as it was slowing down, they've gotten all agitated. They are now moving about, each bristle, sort of, each little particle, with its own little statistical supply of energy. Kinetic energy when it's moving, potential energy when it's bumping into its neighbors and about to bounce back. So what happened to the energy that I invested as work into the box, it's not gone. It's now in a form that we call thermal energy, which is not a new type of energy altogether. It is still plain old kinetic energy and potential energies, energy stored in forces. It's just little bitties of it, all chopped up. It's like, you take an apple or an onion and you slice it up with a knife. It's still all there. It's still, the whole onion's still there. It's just, yeah, your eyes are watering. But it's all chopped up, but it's just fragmented. And that's what happens to the energy when sliding friction does this to energy. When you slide two surfaces across one another, an act which requires work, you do it with your hand. You slide your hands across each other, you're doing work. You can watch, I'm exerting a force, it's moving a distance, everything, okay? there's negative work being done on your hands. Where did the energy go? It goes into thermal energy. You feel the rise in temperature in your skin. If you don't believe that, I've got this guy. Okay, so this is the classic bow and arrow, but no arrow. There's just a stick peg between these two pieces of wood, and I'm going to spin that peg with the bowstring, and the peg's surface is going to rub against the other piece of wood. And this is iffy each year, or sometimes I get it to go. My goal is smoke. I've never managed to get flames out of it, but I usually get smoke. Okay, see the smoke? Woo! All right. I was doing work the whole time. I pushed the bow away from me as it moved away from me, work. I pulled it toward me as it moved toward me, work. Where did my energy go? It went into making that thing hot. And smoke, now I get to breathe it. Okay, you too. Enjoy. All right, so sliding friction, not only does it wear surfaces out, but it actually turns useful energy into thermal energy. And thermal energy has an interesting story behind it. It's the same old energy as always. So you'd think that, well, it's still perfectly good energy. You could do everything you could do with it before it became thermal energy. And the answer about that is no, you can't. There is energy that is work or equivalent to work. And there are a lot of kinds of energy that have that equivalence, that you can turn one into the other. For example, you can use the energy that's in a battery to run a motor, and the motor can do work. So the energy that's in the battery is basically equivalent to work. Maybe some of that sort of like physicist jargon, that it's equivalent to work. It just means that you can do everything you can possibly. It's omnipotent. You can do anything you want with the energy in a battery, with the energy that is in gravitational potential. You lift a big object up high. You can do anything you want with it. You can convert it into all the other useful energies. Thermal energy, not so much. And let's take a look. I think I got the question word for this. Take a look at why thermal energy isn't equivalent to work. Why you can't do the same things with it, even though it's energy. What's wrong with it? And to set the stage for this question, let me show you. Let's look down from this camera at those beads that are in this dish. And I haven't used this guide for ages. Here we go. Yep, you're looking down at the beads. So we've got all the purple beads here on the right, all the white beads on the left. And that's just how we just poured them into that dish like that. And of course, they ended up like that, right? It's already a hint that something's wrong here. Let me stir them. And I'm going to do it without looking. And we'll see whether I can keep that same arrangement. All the whites on the left, all the purples on the right. Stir, 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 stir. Okay. They're not so nicely arranged anymore. They're kind of mishmash. Okay, I'll undo that. Okay. So I'll stir backwards. And I'm sure if I do 3, 2, 1, okay, perfect. It's back where it started. Oh, it's not. All right? So with that, I can ask my question here. And that's this one here. So suppose we videoed that. Suppose we videoed all the white beads, all the purple beads, perfectly arranged as we started, and then I did the stir, and we play the video backwards. And I claim that backwards video, so everything I just showed you, but backwards, I claim that's just what I did forward in time. I did that forward in time. It's not a backwards. It's the real thing. Why would that be all wrong? Why would that look all wrong? Why would you know I cheated? I ran the video backwards. What's the issue here? I can turn them. All right, what is what I need to give you the answer, basically. 5, 4, 3, 2, 1, 0. And the actual answer is C. And here's why. So it was not obvious. It's one of the problems. Scientists, I'm not a historian of science, but scientists have always sort of struggled with what gives the arrow, what creates the arrow of time? Why does everything go forward in time? That things, for example, you build this lovely building and you leave it there unattended for 20 years, it gets gradually more messed up. Things go wrong, and things don't accidentally go right. It eventually decays into nothing. You get Ozymandias there in Egypt. So why does that happen? And it turns out it's a statistical issue. That if you start with orderly things, like the beads, as they were arranged that way, for statistical reasons, that does not happen by chance. I cannot just take the beads and just dump them in there and expect them to go into that lovely ordered arrangement, all white on one side, all purple on the other. It could happen statistically, but the statistics are so against it. Never in your lifetime or anyone's lifetime will it ever happen. So it's a statistical problem. Life goes forward in time because we go from statistically ordered to statistically disordered. Never the reverse. And all the other three choices I have up here are all ones basically dealing with the laws of motion, which are indifferent about going forward and backward. And to give you an idea what that means, because that sounds kind of fishy, the laws of motion are indifferent to the direction of time. Wow, that sounds like something out of a Stephen Hawking film or something. If I have two billiard balls, and I went looking for them and couldn't find any billiard balls, okay? If you watch two billiard balls hit each other, they go bounce like that, off they go. If you run that video backward, it looks fine. You can't tell which direction time takes you in that very simple motion. And that's sort of getting at the laws of motion. Laws of motion, just that objects push on each other, they accelerate, all that stuff. Very simple structures, stuff like that. There's no direction. Forward and backward, the movies would look the same. It's when you come to doing things that explore lots of statistics. For example, along with beads, I happen to have the world's largest collection of dice, okay? So I shake the dice up, and they all come out, snake eyes, a snake den. It's never going to happen. Statistically, it can't happen. But if I ordered them all ones up, which I've done in years past, okay, and I shake it, I will never come back to that order. Similarly, if you beautifully order some objects and you shake it up, it's going to lose the order. You're going to start exploring the statistics and discover that you'll never get back to that lovely ordered arrangement again by chance. And that's, okay, so that gives you the order of time. That gives you the fact that time goes from the past to the future is where it's differentiated by the gradual loss of order. We are big disorderers. One of our goals in life is to create as much disorder as we can. The laws governing the movement around of order and disorder live in the world of statistical physics and thermal physics, and thermodynamics, which is a topic for the other semester. So let me just give you the point here. Thermal energy is ordinary energy, lots of little bits and pieces. The reason you can't turn it back into work, you can't do something simple and interesting like the thermal energy that was present in this box when it skids to a stop, it's still there. Why doesn't it get the box moving and make the box jump to the left? It's because it can't get its act together. It's statistically fragmented with disorder. And to get it to come back together would be like unstirring those beads. It never happens. It's statistically forbidden. Not the laws of motion, but just statistics make it not happen. So hopefully it makes some sense, and look more at energy and thermal energy on Wednesday.